how can a model receive a sentence and produce a relevant continuation, one piece at a time? We will follow the complete mechanism from raw text to a generated response, then connect that mechanism to what language models do well and where they can fail. A language model does not begin with a whole sentence as one indivisible object. It splits text into tokens, words, word parts, punctuation marks, or symbols. Tokens matter because they are the units the model can represent and process. For example, unbelievable can become four tokens: un, believe, able, and the exclamation mark. Think of tokenization like breaking a construction into reusable bricks. The model works with the bricks even when the original word is long or unfamiliar. The model next turns each token into a vector, which is a list of numbers. That numerical representation is called an embedding. The chart uses two dimensions so we can draw it, while the key idea is simply that position carries information about learned relationships. The points for dog, cat, and animal sit close together. Their closeness represents a learned statistical relationship. These tokens tend to appear in related contexts. The embedding therefore gives later stages more useful information than an arbitrary token label would. The other points sit farther from the animal cluster. This does not create a dictionary definition. It creates a geometry of patterns learned from text. Once tokens have these representations, the model can compare them in the context of an entire sequence. An embedding gives a token a starting representation, but meaning also depends on nearby words. Attention is the mechanism that weighs how strongly different tokens should influence one another. Here the question is which words help interpret it in the sentence about a dog chasing a ball. Each value is an attention weight for this example. A larger value means more influence on the representation of it. The dog has a high weight of 0.82, and the ball also has a substantial weight of 0.68, while words such as the contribute much less. Attention combines these weighted relationships so the model can build a context-sensitive representation rather than treating each token in isolation. Before a model can generate useful text, it learns statistical patterns from training text. The text supplies many opportunities to practice the same basic task. Given the tokens so far, predict the next token. This connects the representations we have built to a measurable learning objective. For each training example, the model produces a next token prediction. At first, its predictions can be poor because its internal parameters have not yet captured the relevant patterns. A parameter is an adjustable numerical value that affects how the model transforms its input. The training process compares the prediction with the expected token and calculates an error. It then updates the parameters in a direction that reduces similar errors. The arrows close the loop. More text leads to more predictions, errors, and updates, so useful statistical patterns accumulate through repetition. During generation, the trained model uses the current context to assign probabilities to possible next tokens. A probability is the model's numerical estimate of how well each candidate fits next. This distribution is the bridge between internal pattern processing and visible text. In this example, cat has the highest shown probability at 45%, followed by dog at 25%. Car and house are less likely in this context. After a token is selected, it joins the existing text. The model calculates a new distribution, and the cycle repeats until the response is complete. The same mechanism explains both the model's strengths and its limitations. Learning statistical patterns can support useful language tasks, but predicting plausible tokens is different from consulting a perfect record of reality. Keeping both facts together gives a more accurate mental model. The model's pattern. Learning supports writing and summarization, pattern recognition, translation, and question answering. These tasks all benefit from representing relationships among tokens and predicting fitting continuations. The precise summary is that the model learns statistical patterns. A plausible continuation can still be false, which is why hallucinations are possible. Knowledge can be outdated, small prompt changes can affect the response, and the model has no direct understanding of reality. It is therefore not a perfect database of facts, even when its language sounds confident. Now we can compress the lesson into one left-to-right path, beginning with text. Every pass starts with text from the prompt or the response generated so far. Text is the entry because the later stages need a machine-processable sequence before they can operate. Tokenization converts that text into the smaller units the model handles. The first connection therefore carries us from a human-readable string to an ordered token sequence. Each token then receives an embedding, a numerical representation shaped by learned relationships. This gives the next stage structured numerical input rather than raw symbols alone. The embeddings enter the transformer where attention lets tokens influence one another according to context. This is where separate token representations become a context-sensitive account of the sequence. From that contextual representation, the model calculates probabilities for possible next tokens. The numbers do not certify truth, they rank possible continuations according to the patterns the model has learned. A selected next token is appended to the sequence, and the process runs again with the expanded context. Repeating that cycle builds the generated response token by token. The central mechanism is a repeated conversion. Text becomes tokens, tokens become numerical representations, attention combines context, and the model turns that context into probabilities for what comes next. Training improves those predictions by measuring errors and updating parameters. The memorable takeaway is simple. A language model generates language by repeatedly predicting the next token from learned statistical patterns, which explains both its fluency and its limits.